All right, welcome everybody. We're introducing Sean Smith, branch manager at Polygon Climate Control for today's education session. Sean is the branch manager for Polygon Climate Control in British Columbia, a company that specializes in temporary climate solutions, remote monitoring, water damage recovery, and document restoration in 16 countries across 3 continents. It's a big company there, Sean.
It is.
Before joining Polygon Climate Control, Sean spent 15 years working in the HVAC industry, both in construction, automation, and controls, as well as manufacturing, sales, and distribution of equipment. Sean's focus with Polygon Climate Control is on the engineering and deployment of temporary climate solutions. Considering no one wants to turn on HVAC, that's a pretty important topic right there. Going to be interested to hear what you say about that. Primarily using desiccant technology to precisely control site moisture levels, speed up construction schedules, and eliminate deficiencies. Sean, welcome to the call. Thanks for doing this. Over to you, my friend.
Thank you very much, Chris. Thanks for having me. Happy to be here. So let's jump right into the presentation here. Titled Construction Moisture Management. Might mean a lot of things to a lot of different people. I'm going to walk through what it means to us. Polygon Climate Control has different names throughout the world. So depending on where you are, you might know us or might not know us by a different name. Here in BC, we're Polygon Climate Control. Other parts of Canada, we are Polygon or Polygon Restoration, or if you're from Europe, we're Polygon as well. So there are other names out there. We do a number of things throughout the world as well. We do live monitoring and data collection. So for the flooring industry stuff we're talking about, that's something we do here in BC and all across Canada. And then creating ideal temporary climates. Again, that's what we're going to talk about today. We also do emergency response, water damage, risk mitigation, document drying, stuff like that in different parts of the world. So when I talk about moisture management and how Polygon approaches this, there are certainly other companies out there doing this. We're not the only ones. Everybody's system has some similarities and some differences. I'm obviously just going to speak to Polygon's system. So we measure, monitor, and control. So measurement is done with wireless sensors. They operate on the LoRa network, L-O-R-A. It's a very long-range, low-power network. You certainly couldn't use it to broadcast videos or anything like that. It doesn't have the bandwidth to do that. But it's really, really, really good at reaching long distances with small amounts of data. So we use small battery-powered sensors positioned around the building to measure whatever it is that our customers want to measure. Maybe that's temperature and humidity, maybe it's particulate, maybe it's something else. And all that data feeds back to a gateway, which then communicates with the cloud. All that data is visible continuously in real time from your cell phone, from a computer, for anybody and everybody who wants to see it. Reports, alarms, whatever we need, we can set up. And then we also use that data to control our climate equipment. So whether we're heating a space, we're dehumidifying a space, we're humidifying a space, whatever we need to do, we can use that data, those readings we're taking with our sensors, we can feed it back to our equipment and we can automate control. And the reasons we do that are to know when materials are dry, right? Whether that's concrete or that's wood or that's air. Somebody wants to know when something's dry, and we can tell if it's dry using our sensors.
Sean, can I just ask a question about that? How many sensors do you use every 5,000 square feet or whatever? What's the calculation you use to determine how many sensors you put on the site?
It's certainly very nuanced. I mean, if we're just talking about kind of a rule of thumb, we would take a single sensor for 4,000 square feet. That's if you're monitoring the air, obviously, right? You can cover about that much with a sensor. But obviously, if you're breaking it up into smaller rooms and you're concerned about specific components in each room, or there's not a lot of airflow between them, then that number would rise. But somewhere around 4,000 square feet is kind of a good rule of thumb that we use.
Okay.
So in addition to knowing when materials are dry using those sensors or wet or whatever we're looking to track, we can also prove diligence. So the system is there on the web and we can see conditions in real time, but we can also run reports. All that data just lives in the cloud. So if anybody needs to go back and say, hey, what did your site look like 6 months ago? Those reports are there, right? We can prove that diligence. And we can also mitigate risk, whether that's by knowing exactly what's happening and not guessing at it or preventing user error. The alternative is obviously there's manual measurements out there, right? There's nothing wrong with a nice pin meter that somebody goes around and pushes into some stick framing to figure out if the wood is dry. But that can certainly be time consuming, right? Somebody has to walk around and there's inconsistencies with where are they putting those pins, how hard are they pushing it, right? Those all affect the measurements. Using a continuous system that's in place and fixed provides much more consistent measurements than doing that. Similarly, data loggers, right? They're functional, but you got to walk around back to computer, download everything there. And then our system being automated with our climate control equipment is also provides a lot of savings for time and energy. Nobody's going up to manually turn equipment on and off, and nobody's overshooting, burning gas that doesn't need to be burned.
We've worked on plenty of projects where we encourage the use of this type of equipment, and I can report it absolutely changes behavior, because now the builder feels like they're in control of their site with regards to indoor environmental conditions. And so once you feel like you're in control, you're probably more inclined to sort of put even more effort into maintaining that. It's been a tremendous boost for the industry.
Yeah, exactly. We've had a lot of sites where they can even be uncertain about installing something like this. And, there's a bit of persuasion with, how much are you paying those guys that are walking around and measuring this by hand? The system isn't that expensive. Here's the benefit to it. And, when they come around and it finally gets in place, there's usually this big eye opener of, oh, this is much more convenient. It's amazing. Yeah. How much control we can take of our site when we do this.
Yeah. Someone left the door open on the east wing, half a mile away, because you watch your metrics all sort of drop off, or this, it really puts you in touch with your project.
Yeah, exactly. And this sensor I have up here right now, the multi-sensor, I have literally had this on a site we just set up a few weeks before, and I checked in on them and I gave them a call and said, hey, did you guys notice your wood moisture content in this area really went up? Is there some rain intrusion there? And it was, oh yeah, the windows are out there and it's been raining and they are a bit wet. We're going to get that cleaned up.
Yeah.
So we'll just go over a couple of the sensors we have available. Polygon is very sensor agnostic. We will build just about anything. We've had calls for things like, hey, can we do vibration monitoring? And we will just build a new sensor for that. But we'll just cover the really basic stuff that is more commonly used on job sites. So up first, we have this multi-sensor. It's nice and small. You can see it in somebody's hand there. We've even done away with this big antenna. It's got a much smaller, like half-inch antenna on it now. So very compact. The sensor itself will monitor temperature and RH just on the face of the sensor itself. Just this portion right here. It has optional probes as well. So by itself, if a site just wants temperature and RH, which we see a lot, these would just be installed on a roof, on a stud, somewhere just in the area to monitor that 4,000-ish kind of square feet. Batteries inside, it's going to last about a year, depending on how much data it's reading and how often we want it to report. And if they want to expand upon that temperature and RH, this one can accept probes. So we use this one for wood moisture equivalency, wood moisture content. So it's used in mass timber quite a bit. You can see an example of the probes here. Just a couple of screws drilled in about an inch apart. It's just kind of simulating that handheld pin meter that somebody might poke into a stud. We can just automate that process. Just fix it in place, leave it there. If we go into CLT that's 14 inches thick, we can buy deeper probes. We can extend into the core of CLT to monitor moisture content throughout timber. So that's a super common one we're seeing with all the mass timber push across Canada. We can also do remote temperature and humidity probes. So maybe there's an interstitial space that's cold and damp and they want to know what's going on under there. We can put that probe underneath. We've also got a concrete probe we can plug in there. Surface temperature probe for steel surfaces. If you got some kind of steel substrate where you need a certain temperature on it before you can pour a topping, something like that, we'll use that probe. And it's got a leak detection rope as well. So if we've got an area where we want to track the conditions in the air on a site, but there's also some concerns for, is water going to get in here? Is there an opening in the building and rainwater is going to pour in? This rope can be plugged in, and if water touches it, it alarms. It's going to text people, email people, let everybody know that there's a potential issue there in a certain area. We've also got some more advanced sensors. This is our IAQ Plus sensor. So this can be used to monitor humidity and temperature, but much, much more. So it's got CO2, it's got dust and particulate matter down to PM.5. So that's respirable dust, and it can break up the size of those dust particles in the air. It'll give you VOCs as well. And they can also build in ozone from aldehyde if there's other concerns with some product that's off-gassing on a site. Commonly used to get LEED credits as well, because we can monitor particulate and we can monitor building flush out. And then we've got some leak detection pucks. So a little less fancy than the multi-sensor. There's no probes on this one we can add on, but again, if you've got a mechanical space or some area where there's potential water that's going to get in there, we leave these on the floor, and as soon as water touches them, they alarm. Everybody's notified that there's water there. Again, there's much more sensors than that. That's just kind of the quick high level of common ones we use in construction. And then we take all that data we're reading and we feed it back to our smart controller. So you can see a smart controller here mounted on a piece of equipment, opened up. So this is really just to replace the guys that are having to go outside and turn the heaters on and off, turn the dehumidifiers on and off, and try to keep the building within spec, which inevitably they will not be able to do, right? You're always going to overshoot, undershoot, and you're always going to burn gas or use electricity by doing that, right? So with this system in place, we can switch entire pieces of equipment on and off. We can just turn off portions of them. If we're talking about our dehumidifiers, we'll kill the reactivation cycle so we can still provide air support. and save on energy. So yeah, this is a really great addition we have just to provide savings in addition to the risk mitigation and awareness of what's going on site. The data to look at can look like anything you want it to, really. It's not an app on your phone that's kind of preset where everything's just there. We build these for customers. We're very big on engineered solutions. So this is commonly what we're going to see on a dashboard. So we're going to throw gauges up. This one just shows level 3 on a certain building. It's 21 degrees in there right now. And then we're going to put a bunch of graphs as well that are showing, like a 7-day trend of what's going on with temperature, what's going on with humidity. So this would just be the quick look that people are going to see when they see the data. But then there's obviously a lot more data in the background. So we can also run weekly reports, something like this. If there's a question of, hey, a consultant asked, what happened last Tuesday? We had some water. We can go back and run those reports. There's a lot of stuff we can do with the system. We try to keep it as simple as possible for people that are going to be looking at it daily just for a quick check as to how my site's doing. But it can be very, very complex if necessary. And again, we can also create alarms, unique user logins, whatever customers need, we can build that into the system. We also have a partnership with Wint. So this system doesn't exactly tie into ours, but it all works together. So in addition to just tracking water, say when it comes in from rain or a pipe or a small leak on the ground, you're going to detect that actual physical water. The Wint system is an intelligent valve that actually gets installed on water mains, either a single riser in the building that controls the entire building, or in multiple sections of the building. In construction or even in a finished building, if it's a single line, it would basically be looking for a massive water flow that shouldn't be there. Because the system's intelligent, it's going to learn the water flow of a building. And if it detects a huge inrush, it's going to either immediately shut off those pipes or give everybody an alarm that something's going on and let you make that decision, including people actually phoning you saying, hey, we've noticed this, can we shut this off or is this normal? If the system is used...
Insurance companies love that.
Yes, insurance companies do love this valve. There's a number of case studies we have out there on even just the amount not just the amount you're going to pay for your insurance when you're a building owner, but during construction and your deductible as well. It can all decrease significantly with something like this.
You're seeing strata fees jump like astronomically because of insurance issues around floods that they're getting sick to death of paying out on. I wonder what introducing a system like that into the next build would actually save in strata fees over 20 years.
Yeah, exactly. And even above the insurance savings, it's actually just the savings you can find because of the intelligence built in. So if you had one of these, the east wing, the west wing, a few different places in your building, it'll actually detect essentially a leaking toilet because it's going to learn, there shouldn't be water running at 3 a.m. in this area of the building. And it can detect a very, very low amount of flow that's suspect. So places this has been installed, they're basically able to determine from looking at their dashboard, oh, I have a problem in this area of the building. Let's find out the appliance is dripping. It's a tap, it's a toilet. Just replace those items, fix those items, at least then they're saving on money. So great savings to be had, even if there is no flood, which hopefully there is not.
Is that something a homeowner, for example, could, post-construction, they want, maybe they're the types that go away for a month or something and you're worried about a flood in your home, you could introduce this after the fact?
Yeah, you certainly could. These guys, like I said, Polygon's kind of sensor agnostic. The Wint partnership we have, Wint is kind of hardware agnostic. The valve itself can be really any third-party valve, and then their system ties into it to automate that portion.
Hardware agnostic, what's that?
So if basically you're going to have a valve in your building somewhere. This is obviously more applicable to commercial buildings than it is to residential, but they're going to have some kind of shut-off valve in the building already. Wint doesn't create and sell valves. It's hardware that goes on top of the valve to actually automate that shut-off process. So agnostic in the sense that it doesn't matter what kind of piping you have in the system and what kind of hardware you already have, they will attach into it basically.
I see, yeah. Yeah.
So that's kind of the sensor system. The other portion of what we do is our drying equipment and the science behind drying. So when we're talking controlling site conditions, if you've wandered, this is largely talking about construction, but it certainly applies to really any project where somebody's laying flooring or somebody's doing some work. You might see any type of equipment down below here or a million other pieces of equipment on a job site, right? We got things like heaters, we got dehumidifiers, we got fans. This big guy on the right here is a desiccant dehumidifier. Oftentimes what we're seeing is sites will take a heating only approach, right? They know they need to control conditions on a job site. It's going to be, at least here in BC, it's often going to be wet. It's going to be cold for part of the year. So, that common sense approach is let's use some heat. Heat can help us control conditions. Some people are not aware of indirect fired versus direct fired heat. We'll talk about that a bit later, but the difference being This is a gas-fired direct-fired heater. It just pushes hot, wet air into your building. Something like an electric heater would be indirect fired.
A desiccant dehumidifier is just more efficient than a regular dehumidifier?
Yeah, I've got a whole section on that I'll cover. Desiccant works in just a very different way. So a refrigerant-based dehumidifier like this blue one here, this is what you would see is if your basement flooded and you called a restoration company, like Polygon does restoration in much of the world. If you called them and their basement's flooded, they would bring a handful of these over to your basement, along with some fans, and these would help to dry the place out. This is a refrigerant-based unit, so it's essentially an air conditioner with a heater. So air flows over those air conditioning coils, it cools the air down to a saturation point, right? That water just falls out of the air, drips through a line and gets pumped out of there kind of thing. And then the air gets reheated so that it's usable. So that's a refrigerant unit. Desiccant is an entirely different technology, and I'll walk through that in a couple of slides. But you certainly do see these on job sites. They are functional down to a certain level. If it's too cold, they will not work. And a big thing we're always running into, obviously, is equipment costs are front of mind, right? It's always, hey, I want to control conditions, I want to manage moisture, but I don't want to pay a lot for it, right? I can get a heater really cheap over here, so give me something for that same price. How can I do this? And unfortunately, there's some detriment there with there's little consideration given to the cost of delays or deficiencies, right? Sure, a heater works, it heats up air, and it can cause some drying, but in many cases, it's much more efficient to use something like desiccant technology. Even if it's more expensive than a single heater, it can do it much quicker and ultimately be more affordable in the long run. So again, this is somewhat targeted to construction because that's a lot of the industry we're in. So moisture infiltration on the job site, you're going to have buildings going up, like this picture here. You've got weather coming in. They can't control the rain. We're not going to build under a tarp all year, right? So you're going to get rain coming in. Timber might show up to site at 19% moisture content, but it's going to get wet during the process, whether that's from wet air or actual rainwater. So it's going to add some water to the building, and it's going to get enclosed, and that water is still going to be inside. There's other materials as well, obviously beyond wood. So you've got things like concrete slabs. I know we're talking to the flooring industry guys here, so I'm sure you guys are well aware of the fact that concrete has moisture in it, and it releases that moisture even beyond 28 days potentially. We've also got things like joint compound and paint, right? Those go on wet and they dry. As they dry, they evaporate. And as they evaporate, they increase vapor pressure. I got this highlighted here. We're going to cover the science of this in a bit, but that's the big thing that we control with desiccant dehumidification is vapor pressure. And that's something that other means of heating and cooling don't really affect. So when vapor pressure is high, materials can't dry. So vapor pressure, just for quick reference, means it's the pressure that water molecules exert on one another in the air. So you can't see that happening, but if you were just to cut an imaginary block of air out and hold it in your hands, there's a certain amount of water vapor in that air. And those molecules are bouncing around. And the more of them there are, the more pressure they exert because there's more of them there. So when vapor pressure is high, meaning there's a lot of water molecules in the air, wet materials have a hard time drying. So lumber, obviously, this is a real worst case scenario. If you let wood stay wet for a real long time, it can rot, it can break down. Something like 28%, it will actually start to decay. You could get mold, right? You could have a real bad situation if you let things get that wet. Even just a bit of water that's less than that 28%, you can get cracking, you can get warping, right? But there's other things too. There's like joint compound, it might dry very, very slow. It could be 2 weeks of drywalling on a job site and everybody's getting upset for why it's taking so long. They're adding more and more heat, but they have so much moisture in the air. There's such high vapor pressure that those things can struggle to dry.
That's that 28% is basically saturation, is it not?
Yeah. So at 28%, your free and bound water in the wood is essentially full. It can't hold anymore. So it's half wood, half water at that point kind of thing.
Yeah. So I've got a sort of a reading that would mean someone installing wood flooring over plywood could proceed on is 12%. So it gives you a sense of, twice the amount of moisture there is going to cause a lot of problems.
Yeah, exactly. And I mean, there's plenty of sites that get up, almost to this level during construction, and they're able to dry out just fine, but it's definitely a danger zone if things get that wet. So here's the quick and dirty of psychrometrics. So psychrometrics is the study of air and water vapor. So it's about 1% of air that is water vapor. It's a very, very small portion of air. And I already mentioned that water vapor pressure is that force that water molecules exert on one another. So psychrometrics tells us that water vapor always moves from high pressure to low pressure. And it's always seeking an equilibrium. So it's basically thermodynamics. So if you look at this very simplified diagram here, imagine you have a material, you can call it wood, you can call it concrete, it doesn't matter what it is, but you have a material and there's a certain amount of water in that. And then you have air that's going to be touching that material. And it also is going to have a certain amount of water vapor in the air. When they're at equilibrium, they have the same amount of vapor pressure. The water is not going to move between them. The vapor pressure will be the same. They're at equilibrium. They don't need to move. There's no pressure differential. Now, equilibrium could be really, really low, could be really, really bone dry, could be somewhere in the middle. It could be soaking wet. It could be that 28% moisture content level in wood and really, really wet air surrounding it. And even though that wood is so wet that it's a problem, it can't dry because the air is so wet. So we need to create a non-equilibrium situation in order to get water to move. So if we can lower vapor pressure in the air, we can essentially force materials to dry. And the greater the difference we can make in materials, or the greater the vapor pressure differential, the faster we can make them dry. So just using that same example in the other corner there, if you have a really wet material and a really dry air, if we can, this red bar is kind of showing dehumidification. If we can force that air to be drier than it normally is and throw this equation out of balance, create that vapor pressure differential, all the moisture that's in the material is going to get sucked out into the air until we reach an equilibrium state. So this is how desiccant technology actually works. So I mentioned earlier those little portable dehumidifiers are commonly an air conditioner and a heater packaged together, and they do work to remove some water, but this is a very different technology. So desiccant is those little packets you get when you buy a new pair of boots. Shiny new boots, and there's a little tiny packet that says "Do not eat." It's going to be silica gel commonly. So silica gel is impregnated on this wheel. It's not a small wheel. Some of this equipment is very, very large, but there's this big wheel with a honeycomb structure. It looks kind of like a cardboard, and you can see through it. And that cardboard honeycomb structure is impregnated with that silica gel. Silica gel has a very, very low vapor pressure, meaning water is attracted to it. So it actually adsorbs water. So it doesn't absorb it. It doesn't turn it from a vapor in the air into actual liquid. It remains as water vapor. It maintains its state, and it just sticks to that silica gel. So this wheel's inside the machine. Process air is the air we're actually using. So we basically take outside air that could be reasonably dry, could be soaking wet. I'm in BC, so air here is often 80 to 90% relative humidity. We take that wet air and we just draw it through the wheel, and that silica just grabs all the moisture and holds onto it. And so you get this stream of super, super dry air. If you're measuring it in relative humidity, it's going to be less than 10% RH is kind of the rule of thumb. Now, eventually this wheel would be totally full of water because that silica can only grab so much water vapor, and then it would be useless, right? You'd just be pushing air through a wet wheel and the wheel wouldn't grab any more water. So to reactivate that wheel, there's a heater. It might be gas powered. It might be electrically powered. We're going to have another air path that we're not using this air. This is just to refresh the wheel. So we're going to draw some air. We're going to heat it up, and then we're going to push it the opposite direction through the wheel, just through this one little section here that's kind of cordoned off from the rest of it. And by doing that, we basically wiggle all the water molecules loose and just blow them outside. So this wet air portion is basically like your dryer vent at home. You put your hand in front of it, it's like steamy and hot and wet. That's the air we're not using. So that's all the water we've stripped out of the air to give you this dry air stream. So really all we're doing is just robbing the air of its moisture and then providing this continuous process. It doesn't slow down. It just carries on and on and on with this low vapor pressure air. And then what we do with this beautiful building in this drawing here is we blow that dry air into a building. It's as simple as that. Because it's really, really low vapor pressure, it forces moisture out of everything. So if this is a building under construction, or they're painting and there's all this water that's leaving these products and going into the air, we create this big differential. Our super dry air meets the wet materials and wet air. The moisture gets picked up by the dry air and we force it out of the building. So on a construction site, there's commonly cracks or there's doors open, and that air just flows out naturally. We just create a slight positive in the building to force that moisture out. If it was a totally finished airtight building, then we would just open some windows. We could recirculate the air back through here. There's a few ways to go about it, but this is just the most simple way to look at it. We push in the dry air, slight positive pressure. It forces moisture out. The moisture leaves the building.
Can you be very accurate with your humidity levels within the building using that equipment?
Yeah, we can. So that kind of goes back to the original slides with the sensors, right? So if we're not monitoring, if we're just pushing dry air, the machine is going to push dry air all day long until it's very, very dry in there and somebody turns it off. But if we have sensors in the building and we want to target, say, 40% relative humidity or 50 or 30, some processes are just looking for a dew point separation. Whatever we want to target, if we have sensors there, we can see what's going on in the building, and then we can automate control of the equipment to make sure we're not overshooting.
That's great, because the millwork doesn't like to be too dry, right?
Yeah, exactly. That's the big thing, right? It's, again, you could turn it off yourself and hope that it's within spec, but it's certainly a lot easier to monitor the conditions and then just automate control. And this is what it actually looks like. Again, it's quite simple. This here is a desiccant dehumidifier. The portion on the left is actually just a gas-fired add-on, but commonly you would just have this piece here, a desiccant unit. This is that process air, that dry air outlet. And in this case, it's pushing through an indirect fired gas heater because they have a heat requirement as well as a moisture requirement. And then this ductwork just runs up the side of the building. This is a multifamily building, obviously. They've just taken out a window here in this hallway and they've just popped the ductwork in. So you've got all these levels here. Each of the hallways has this lay flat poly. This one's actually deflated. They had a dust concern at the time, so they just tied it off with some twine. But normally this poly here would be inflated, a nice round, super buoyant, super lightweight poly duct. It's perforated. It just sprays that dry air all over the building. Because all the air is touching, it's going to distribute fairly well without having to have the ductwork run into every little nook and cranny. We can add fans, things like that. But really, we just want to distribute that dry air throughout the building to force those materials to dry, to force everything to give up its excess moisture.
And basically the motivation here to do this is because HVAC can't be turned on.
Yeah, exactly. I did work in the permanent equipment industry for a while, and yeah, if somebody said to you, "Hey, we're going to turn on your rooftop unit, we're still under construction," we would laugh and say, "There goes your warranty." Some sites might be allowed to turn on their permanent equipment, or if it's a building that's redoing something, they might be able to. But there's commonly a concern with dust that's going to get trapped in those filters and damage. So yeah, most construction sites are not even going to have permanent equipment, and those that do likely won't be able to turn it on.
Yeah.
I guess the other thing to point out with that is that your average permanent equipment won't actually have a desiccant dehumidifier in it. Your rooftop may have a dehumidification feature by the air conditioning, much like those little portable guys, right? So they can sometimes remove some moisture, but the moisture load you can create during construction is potentially much, much higher than a permanent system could actually remove anyways.
Yeah, and in flooring, we don't really care how you do it, as long as you got somewhere between 40 and 60%, roughly. You're going to be okay for your humidity management. You got that 20% range of what is okay.
Yeah, exactly. Right. Like you said, it doesn't matter how you get there. And if guys can get there by opening the windows and using some fans, then great. Right. You don't necessarily need desiccant technology. Where I am in BC, it's definitely tough to get it naturally. The air is quite wet. But this is why we engineer solutions, right? We're definitely not a catalog of here's the equipment, pick what you want. We are very much a look at the site. What are the air conditions? What do we need to do? Is it heating? Is it dehumidification? Is it nothing? Is it fans?
Yeah.
So here we've got kind of a combination of our desiccant equipment and our sensors on a job site. So this is a student housing building. It's on the go right now. It's under construction. So when we first got there to put in sensors, our dehumidification equipment was not set up. So we got the sensors up ahead of time so we could track conditions throughout the project. So you can see the relative humidity levels here. This is just essentially outside air. The building is fairly open. There's a lot of windows not there. And even on the floors where there are some windows on, the upper levels are still open. So there's a lot of outside air infiltration. And we're in BC, so we're at about 80–85% relative humidity. And this was back in November. So very wet, temperature-wise. It looks like it wasn't too cold. It's somewhere in like the 10-degree range. The sensors are monitoring temperature and humidity. It's those multi-sensors I showed. And then they're also monitoring wood moisture content, though the wood moisture content is not actually shown on here. So this drop right here, that's really all I'm trying to highlight. This is when the desiccant dehumidifier started up. So it's connected, much like in the previous slide, desiccant dehumidifier into a heater and then into the building, just for a minor heat gain. So you see they get a bit of a heat rise, which is both from the heating equipment, and there's a slight heat carryover on the wheel because of that reactivation portion where we're removing the water. But the temperature is not important here. It's really just the temperature rises a little bit because they had a certain temperature requirement, but you just see this massive, massive drop in relative humidity in the air, right? Going from that 80-ish% level down to 30% in this one, 50% here. So depending obviously on where they are in the building, probably the sensor that's a bit drier is a corner that's more tight and getting a bit more dry air. So maybe need to adjust the ducting to get things back in that kind of 50% range. But you can just see this massive, massive drop.
Well, now materials are starting to dry.
Yeah, exactly. And this was mass timber. So the wood that's there would have come to site with a certain moisture content from the factory. But as soon as the factory puts that wood on a truck, it's somewhat out of their control, right? They're handing off a spec that says, your timber needs to be at 18%, give or take 2%. This is your problem now. And then as they're building, right, that wood is getting rained on. Again, this is in BC, it's a rainforest, so it's getting soaking wet at times. And these guys were great. They had a crew there squeegeeing and vacuuming and getting that bulk water out of there. But there was absolutely a time I walked those floors and there was an inch of water on them that I was walking through. That's just the nature of construction. So once we can close that up and get that dry air in there, that really, really low vapor pressure, all those wet materials just have to give up that excess moisture. And then I've got a note here too that if you were trying to achieve this same RH change using heat alone, you'd actually have to get about a 15-degree heat gain as opposed to this desiccant drop we get here. And you would have no change in vapor pressure if you did that. You'd have to crank up the heat like crazy, burn a lot of gas, use a lot of electricity, but you'd still potentially have the exact same vapor pressure between your air and the materials. So there's no guarantee you would dry, even if you managed to achieve this kind of drop in relative humidity by using heat.
That's interesting. 90% RH at 8 degrees Celsius. It must just be an atmospheric river outside.
Yeah, I mean, that's BC. Today, I think last time I checked, it was somewhere in the 80s on a couple of my sites, and it's a bit warmer than 8 degrees. But yeah, it's rainy, it's wet here, right? It depends on where you are in the world, and that's why I think I've got another slide. There it is. Engineered solutions.
Let me just comment one thing. So in flooring, we care about that because if you're trying to trowel out a water-based adhesive with 90% relative humidity, it's just not going to cure. It's just going to be a mess.
Yeah, for sure. And so the reason this slide is here with engineered solutions is to kind of highlight the weather's different everywhere and you need to know what kind of air you're working with. So like you're saying, if you're trying to trial a product and it's 90% RH, it's not going to dry. You're in for a bad time, right? You're not set up for success. So we run weather calculations for every project to figure out what is the air going to do. Air changes throughout the year. We want to know how much moisture is actually in that air. What's the temperature of that air? So this is just a psychrometric chart. It looks super, super complex. It's not that complex. You've got temperature on the bottom, cold is on the left, hot is on the right. These curved lines are your relative humidity lines, right? So as you get hotter, relative humidity drops because hot air can hold more moisture. Air expands. Its ability to hold moisture grows. And then over here, you've got absolute moisture levels, which is not something people commonly look at, but that's super important for vapor pressure and for engineering this stuff. But the point of this is just to highlight the calculations that we'll run. So these dark blue areas, these are areas in the year where there's a few hours a year that are that temperature and that moisture level. So this is in Fahrenheit. So, 30 degrees, it's quite cold and down in the 30% relative humidity. In Vancouver, there's not a lot of days that are in that range. But these red areas, this is where there's a number of hours throughout the year that there are these conditions. So, in the 42, 44 degrees Fahrenheit range and 90% relative humidity, there's a lot of days in Vancouver that are sitting there, right? So we want to look at this. We want to analyze where the job is and say, what's the air we're actually working with? Is it 90% relative humidity all the time? Or is it 5% relative humidity? And is it very cold? Because once we know that, then we can properly size equipment and properly plan for a solution. So this is a simplified version of the chart. And this is kind of the culmination of all the stuff I've talked about with vapor pressure and different methods and what people try to do on site. So again, we've got temperature on the bottom. This time it's in Celsius because we are in Canada. These curved lines are still relative humidity. They're a bit easier to see. And then over here is absolute humidity. So this is the actual amount of moisture. This is in metric, so it's grains per kilogram. I'm usually going to talk grains per pound. That's the imperial measurement for it. But this is the actual grains of moisture that are in air. So this blue ball is just meant to represent a bunch of water vapor in the air. So these blue balls are not necessarily mathematical calculations. It's just kind of highlight the different ways that people go about managing moisture on a site. So if you have a site and your air is 20 degrees Celsius and 50% relative humidity, that's the curved line here, you've got this blue ball of water, right? Your site is wetter than you want it to be. You want to control conditions. You've got flooring going in. There's a spec you need to meet. How do we control that moisture that's there? So if we use a direct fired heater, now I mentioned that I would explain this. So a direct fired heater is going to be a gas fired heater. That could be natural gas, that could be propane. But you're basically lighting gas on fire and you're taking air and you're pushing it through that flame. There's no separation of the air and the flame. It's just flowing through it. It's taking all the products of combustion and it's moving them right into the space you're using them. So, if you're thinking about it as I talk about it, it sounds like a bad idea, and it definitely is. Products of combustion are harmful for you. But this is a common way to heat buildings. In some areas that are really dry, they actually really love this because it adds water, but you're still getting CO and CO2 and things that are not great to be breathing. And you can see this blue ball going from this condition to this condition using direct fired heat has gotten a lot bigger. So I'm just doing that to show you that when you're using direct fired heat, you're adding water. A quick and dirty calculation would be if you had propane fired heaters on a site For each 100,000 BTU that they're rated at, you get about 3.7 liters of water per hour that's being directly pushed into the air that's going into your space. So if you had a 350 kBTU heater, it's a super common size, and you ran it 8 hours a day, you'd be adding 103 liters of water to your job site every day. So these sites that are going, hey, I've got moisture, I want to control it. I rented a bunch of heaters, I put them on each floor, and I'm firing them off. This is what's going to happen. They're going to gain all this water. Now, the confusing part is that when you move this way on the chart to the right on the psychrometric chart, your temperature is going to increase. So you might go from 20 degrees to 50 degrees. It could be smoking hot in that building, right? They're heaters, they produce heat. And as a result, your relative humidity is going to drop because air, as it gets hotter, can hold more and more and more moisture. Your relative humidity could go from 50% down to 25%. And you could be patting yourself on the back saying, hey, like, look how dry I made this building. I used these heaters, they were cheap, it worked really well. It's really, really dry in here. In reality, your absolute moisture level, and this is basically directly correlated with vapor pressure, your vapor pressure has increased significantly. So you've gone from this little blue ball to this big blue ball. Measured in grains per kilogram, you're somewhere, from 7 grams per kilogram up to about 17. So you've now increased your vapor pressure, which means that if your materials have less vapor pressure than that wet air you're making, the materials are going to take that moisture and they're going to suck it up. They're going to absorb it. So you are potentially creating a massive problem for yourself. Despite the lower RH, it's kind of an artificial lowering. Everything could actually get a lot wetter on your site. Now, if we compare that with indirect fired heat, again, that could be a gas-fired heater. It could be electric as well. But if it were a gas-fired heater, again, it could be propane or natural gas, you're going to burn that gas inside of a heat exchanger. And the products of combustion are going to go outside. So there's going to be a stack on top of it, right? There's going to be a flue pipe, and you're going to take all that CO and that CO2 and that water, most importantly, and you're just going to push it outside. So you're not going to use that stuff you don't want in your building. You're just going to push air across the heat exchanger. It's going to do sensible heating. It's going to pick up the heat from that heat exchanger, and it's going to push it into your building. So
just as a side note, Sean, as you're burning those those propane heaters, a byproduct, carbon dioxide, is going to, if you have new concrete poured, that carbon dioxide is going to interact with the surface of that concrete and cause it to dust all day long. So you wonder why you can't get rid of the dust. If you're burning propane, you've got a moisture issue and you've got a dust issue.
Looks like I learned something today too. That's actually that's fascinating. That's not one that I knew. Yeah, it's definitely one that we push people away from for other reasons, but I guess it's one more for me to to add to my list.
Yeah.
So yeah, if we use this indirect fired heat, right, rather than getting all that CO2 and all that stuff that Chris is talking about, we're just getting heat. So we're going to rise, again, we could go from 20 degrees to 50 degrees. We can make it very, very hot with an indirect fired heater because it's a heater. It's really good at heating air. But your little blue ball here is going to be the exact same size. Again, your relative humidity will drop because you are expanding that air. As that air gets hotter, it grows, it can hold more water. So your relative humidity might drop to 10% RH. And again, somebody might look at the site and go, hey, we did a good job, it's dry. But again, your vapor pressure won't have changed at all. It has the exact same amount of water as it did before. So if your vapor pressure in the air is the same as your materials, they're not going to dry. Heat can cause evaporative drying, right? You're going to get some water molecules near the surface of something bouncing around, moving up into the air. So you can still achieve drying with heat. This is not to say that heat will never work to dry. It's just to point out that dehumidification is more efficient at it. So again, direct fired heat, adding water, indirect fired heat, not affecting water. And then desiccant dehumidification is basically directly targeting moisture. So we do move to the right when we use desiccant technology because there's a heat gain on the wheel from refreshing that wheel and pulling the water off. The wheel warms up and then the air picks up some of the temperature. So while we will heat up, that's not the purpose of the equipment. The purpose of the equipment is to remove moisture. So we're just essentially moving downwards on the graph, right? Again, not scientific numbers here. We're just kind of giving a representation of this blue ball is shrinking. It's getting much, much smaller. Our vapor pressure, our absolute moisture over here on the right is significantly less. So by doing that, we're creating that air with that really, really low vapor pressure. We're going to force everything to dry.
Love it. Cause and effect.
And then this is really just a summary, right? So, I mean, this is the stuff we're talking about. Flooring, millwork, other materials on site, right? Concrete has moisture. How do you get the moisture out of there? You've got to wait your 28 days. But even beyond that, right? Is there still too much moisture? How do you get it out? Some guys will use heat. That can take a long time. It might not work. Desiccant dehumidification does an excellent job of removing moisture from slabs. And then obviously with materials, right, you can maintain stability. You've got to acclimate materials on site. they can sit on site and you can stick a pin meter in them, check on them, see how they're doing. We can also just put a sensor in there, provide continuous data for, what's the moisture content of that wood flooring that's sitting there, and as well as provide a record of the air. We've maintained conditions throughout construction. We know where it was stored for this amount of time. We know that it's ready to go. We're maintaining the space while it's being installed. So a lot of benefits, obviously, to directly controlling humidity as opposed to just heating and hoping that humidity is where you need it to be. And really, we're just trying to create the climate at which that woodwork is going to spend its service life, right? That permanent rooftop equipment that's going to be in place at some point in time, it's been engineered and spec'd out to hold conditions within a certain range in that building. And we're basically trying to recreate that range when we're using equipment on site to control conditions. And then the exact air system as well. In addition just to that record of diligence, it's also proving things like deficiencies are not from workmanship, right? If you've got some flooring that was laid and something pops and twists and cracks, and somebody comes back and says, hey, you installed this wrong, obviously something you did cause this problem, but or you didn't keep your building within spec. You've got that record to show, like, no, the building was within spec. We were within 45 to 50% throughout the life of this project, 45 to 50% RH, say, for example, in this temperature. So you can prove that there was diligence there. So slightly different from flooring, but this is just some third-party data from the Wall and Ceiling Bureau. So basically, these are the drywall guys, and they put out this chart and said, if you want to be in this ideal green zone, desiccant dehumidification is the answer. And they're just comparing temperature and relative humidity, right? So if it's freezing cold, 32 Fahrenheit and 98% relative humidity, theoretically, mud will take 53 days to dry. Unlikely you'd ever see a job site that was in that position, right? But that's the science behind how long it would take for that mud to dry. Desiccant dehumidification is going to push out air that's in this 10% range, right? So we're already sitting down, assuming it's 50-ish degrees, 21 hours for mud to dry. So these guys can literally come in the morning, first coat, heavy coat. They can come back that afternoon, depending on how warm it is, and sand out and recoat. Versus a heating only approach, if your air is quite wet, even if you get it really, really hot to achieve these similar kind of 14-hour, 10-hour times, you have to make your building 90 degrees, 100 degrees inside, which is not practical for your average construction site. And we'll finish just with a really simple real world example of how desiccant works. So this is a site in Greater Vancouver here from a few years ago. So there's concrete on the ground. It's beyond its 28 days, but that concrete is still giving off some moisture. It's still a little bit wet. We've got drywall we can see in the background with mud. So they got water there. Not pictured is there's also some cementitious fire stop that's been sprayed everywhere. So that goes on wet, it dries, water evaporates into the air. So they got all these things adding water into the air. And you can see these windows here, right? They're covered in condensation because that air, when it touches the window, it gets even colder, it shrinks down, it can't hold all that water it has in it because it's already saturated, and that water just sticks to the window. So the solution was, let's heat up the building, right? It's wet. If we heat it, we can dry it up. We can get this moisture out of here. So you can see all these propane bottles scattered around. And this one here, you can actually see some flame on the end. So this is a good example of the most simplified direct fired heating system you can imagine. It's a bottle of gas with a regulator and a flame on it. So as they're doing that, they're pouring water into the building. And it was actually very warm in here with all these heaters running, but it's very, very wet. It doesn't matter how much you drag them around. You're just adding more and more water in there. It's like trying to drain a pool by dumping buckets of water into it. It's not working. So these guys had trades going home. Work was essentially at a standstill. This is a single desiccant dehumidifier. This is a 4,500 CFM unit for this fair-sized warehouse. There's a single piece of duct. This is pushing that dry process air that's less than 10% RH into the building. And you can see a nicely inflated, like the poly tubing. There's some holes here. It's just perforated to spray the air around. Oftentimes we hang this from the ceiling, route it to different floors. In this case, there was nobody there anyways. Just laid on the floor, spread that dry air out. And you can see the windows in the background, totally clear because the moisture is gone, right? We're not adding heat and hoping that it's going to evaporate. We're adding dry air. We're forcing the moisture out of those materials, the moisture off those windows, and we're forcing it out of the building, and we're dry. And that's it. That's the end of me, Chris.
Oh, that's great information. I'm going to open it up to the floor there. If anyone's got a question for Sean. While you think of your questions, I've got an observation. That last slide with the condensation on the window, that for flooring concerns us greatly, because if we're trying to trowel out water-based adhesive on the concrete, you can get the exact same condensation point, we call it dew point, form on the concrete surface. You don't see the moisture like you do on the window because the window is impervious, but the concrete absolutely will soak it up. and become a great cause for concern, saturate the surface overnight or in very short order, actually.
Hey, I've got a quick question for you, Sean. My name is Bob, and on this slide that you've got there, what do you use the poly for? Is that to distribute the air, or
Yeah, that's for air distribution. So, I mean, we could literally take this yellow duct and just poke it in one corner of the building.
Right.
Some guys will comment, if you pull the plug out of a bathtub, everything's going to drain. So we certainly can just push air in the side. But in order to properly mix that air and just make things faster, yeah, we commonly then would connect this poly to this yellow tube here. We'd run the poly throughout the building, and it's perforated. It's just to distribute that air throughout.
Oh, I got it. Okay, got it. Thank you.
Yeah, that was great information. You mentioned the direct heaters that restoration companies use when they have a water leak or whatever. So that's essentially, just null and void. They're just continuing to put water back into the property that they're trying to dry out.
Yeah, if somebody was using direct fired heat for restoration, that would be far from ideal. I mean, again, you can dry with heat. I mean, I'm not going to lie and say I've never seen somebody dry with direct fired heat, but it is adding a lot of water to the equation, and some people just don't recognize that.
And the desiccant, is it? I'm familiar with it. Did you say silica? Is that silica?
Yeah, it can be a number of things. It can be titanium silica. It's commonly silica gel, is what's on our wheel. It's available in a bunch of different formats.
Yeah, back in a previous life of mine, I worked with sugar. As a pastry chef many years ago when I left school, and we used to use silica gel to store sugar work in sealed containers to stop the sugar absorbing the moisture and essentially melting. So it's a similar product, I'm guessing, it's doing a similar thing.
Yeah, exactly. It's just it's being used a different way. Yeah, that silica is impregnated on the wheel that's inside the machine, as opposed to being in a bucket or a sachet or whatever that's protecting the sugar. Yeah.
So sure. Wow. And another desiccant, Sean, would be calcium chloride that we find in the moisture vapor test.
Right.
Yep, exactly.
Interesting.
So Sean, it's Drew here, calling from Toronto. Instead of putting a humidifier into a system, is to creating the vapor pressure, is your system the same concept of putting dry air into an environment to push it out of all the leaks in the building? But by adding a humidifier, is that not the same kind of concept of drying the air, creating a vapor pressure to dry out the materials? Yours is just a super system of a dehumidifier. I just want to make sure I'm on the same page as dehumidification. You're putting dry air in, and a dehumidifier would be drying air. Just explain the differences, or am I on the right concept?
Yeah, so I mean, the desiccant equipment is dehumidification equipment. There's no doubt about that. It's nothing different. It's just a different style of dehumidification. I'm going to bounce back to this slide for reference. Yeah, so like the desiccant dehumidification is dehumidifying air by removing moisture, right? And we're pushing into a building to force those materials to give it up. If you compare it to like one of those restoration style refrigerant dehumidifiers, that's not pictured on here. So a refrigerant-based system would basically take this blue dot, and it would make the air colder, colder, colder till we hit this line, because this is our saturation point. This is condensation. And then it's just going to follow this line down until it can't cool anymore. Then it's going to reheat it. And so you're going to end up somewhere down here where you are drier and maybe a little bit colder. So it's just this kind of C-shaped direction for refrigerant-based dehumidification. But yes, our system really is just dry the air out, push it into a building, and force the moisture out. I mean, if the materials are already dry, if we're talking a site that was built 20 years ago and they're just redoing the flooring or something, and we just need to control the air conditions, it's obviously a bit easier. We're going to use smaller equipment, and we're just going to monitor the space that we're trying to control, and then automate the equipment to make sure we're maintaining whatever relative humidity levels they want.
Okay, great. Thank you.
The desiccant machine is almost scrubbing the air of moisture.
Yeah, that's exactly it. Because the wheel just grabs the moisture out of the air and holds onto it. So it is stripping the air of moisture. And when we use this in, so if you know, like the shipyards here in Vancouver, we've got some equipment that's being set up there today. So when they are painting the hull of a ship, obviously it's steel, they're going to blast it down to bare metal. And if they can't control the moisture in the air, it's going to rust instantly. You won't see that rust, but as soon as there's moisture in the air, that steel is going to rust. So they would actually then recirculate the air through the machine. So they're going to constantly be taking that air and drying it at all times. And that allows them to blast things down to bare metal and gives them enough time to prep it and then paint it, coat it, whatever they're doing without any rust formation.
Wow. Do they do just sections of the hull at a time, or do they encapsulate the whole?
It can certainly be any of the above. This particular one, they've got poly kind of taped around the bottom portion of the hull. So I think they're doing the entire bottom section, but it's certainly not the entire height of the ship.
And what RH do they have to get it down to?
I don't know if I have a spec on that job exactly. I think they want to be typically in the 40% range.
Oh,
It's more about it's often more about dew point separation as well, with the surface prep and coating industry, obviously.
right. So you can have vapor touch the surface, but you can't have it condense into a liquid.
Absolutely, yeah. You can have a certain amount of moisture in the air, and it's still going to function without rusting. But yeah, if you hit the condensation point, then you're in for a real bad time, because then you absolutely have rust on that ship you're trying to coat.
Right. Okay. Interesting.
So,
Because
Sean, in regards to what Chris said, your machine scrubbed the air, the moisture. I understand that, but it's scrubbing outside air and pushing the drier air into the building to cause a positive air pressure. Versus a dehumidifier would be taking the indoor air and scrubbing it of its moisture.
Yeah, unless we recirculate, like I mentioned with the boats. So if we were just supplying outside air, yes, we'd be doing positive pressure. If it's a situation where we don't want to do that, we can't do that, or there's tighter control, then we would recirculate the air, much like a refrigerant-based one you're talking about.
Okay.
So the equipment might still be outside, but in that situation, we'd be taking the outside air, scrubbing it, and recirculating it back through the building over and over again.
Okay.
Very interesting. Any more questions from the group? No? Sean, looks like you might be close to getting off the hook here.
Talk fast and leave little room for questions. I know the drill.
Hey, dense information, like very lots of great information. Love it. So, well, let's unless someone wants to ask a quick question, we'll wrap things up and let you go. Sean, thank you so much for doing this. For those who are still on the call, everyone's going to get a copy, a YouTube link to our YouTube library, where there are countless numbers of sessions like this on all sorts of topics, typically related somehow to flooring. Anybody can access those that library anytime for no cost. We're just trying to raise the bar here in construction by putting out great information from subject matter experts like Sean. So, Sean, again, thank you very much.